Thank you. So I've titled this presentation Games for Research and Research for Games because I'm trying to cover a lot of topics so it doesn't get too boring for all of you. So as a brief outline, I'm going to talk a bit about myself, and then after I'm going to get to the games for research portion of this, and then I'll also talk a little bit about like Unity tips. I know Unreal is being used a lot more at EGS than it was when I was there. So some of it won't apply, but most of it's pretty applicable to both engines. And then after that, I'm going to talk about research for games and a little bit about my work. And that should be about 40 minutes, hopefully a little less, and hopefully it's not too boring for everyone. So a bit about me. I started it at EGS around 2013, and that picture all the way in the back is about 2013 when I was there, maybe 2014. I graduated in 2017, which is the frontmost facing pictures, and I'm exceedingly excited about it. After that, I went to University of California, Riverside Brain Game Center, and that's where I'm going to talk a little about games for research and how they can be used. And then after that, I went to Northeastern to work on my PhD. While I was at EGS, I think the only notable thing I did was I did the Tetris project. So I imagine there's at least one of you in this crowd back there that has to maintain the code or work with it. And so if it's really bad, I apologize. Hopefully not too bad. And the only other thing is I'm an uncle to this crazy little girl right here. And my nephew is actually off the picture, but that's okay. And then this is my dog, Maggie, who, I don't know if like it's very visible, but this is her. She's a crazy dog. She's 50 pounds, a little shy sometimes, at least camera shy. And yeah, so hopefully that little bit of cuteness will hold you off for the rest of the presentation. And I'm going to talk about the UCR Brain Game Center. I skipped the section of games for research and Unity tips. And this is Aaron Seitz, and he's actually a friend of Frank's, and he's the one who created the Brain Game Center, or BGC for short. And they're occasionally, I think they have 3 full-time programmers and 1 part-time. And for like a university lab, that's pretty insane, as I'm sure you guys can understand. So if you do have the opportunity to work for him when you're graduating, I would recommend it. It's a really nice place to work. And what he's trying to answer at that lab is the question, can games improve cognitive functions? And if you're looking for a good opinion, I bet you Frank can give you one. But the basic way you go about answering a question like that is you give someone a game, such as Among Us. Just Maggie. Sorry, something caught our attention. So you give them a game like Among Us, and this is a really simple memory game where you have to remember the sequence of buttons. And what you want is you kind of want transfer. So if you had someone play this game for 5 minutes for 10 days, after that point of time, would they be able to play something else? Like, I don't know, memorize this random sequence of strings or words, better put. And if there's transfer, then you're getting at something good, but most of the times you're really not. So the core question is, how can we design games to try to facilitate transfer learning? And that's a whole research topic in itself, and that's what the Brain Game Center is trying to do. And the way they're trying to do that is they have 8 different games that they maintain. Some of them are no longer that much in use, like this little BA one. This is called Remember B, and that's not in much use anymore because it was a memory task that has been replaced by this game called Recollect on the left with the space person on it. And this actually leads to a lot of technical challenges when you're working at the Brain Game Center. So even if we're not talking about games for research specifically, there's still a lot of technical challenges in maintaining it in terms of configurations and whatnot that I'm going to get at. But when you're actually running a study for this kind of thing, the basic process is you're going to have someone design the study, postdocs, PhDs, maybe a master's student, but kind of rare. Then the programmers are going to implement the study's protocol. So if you're programming your game well, then your game is already configurable. But if you're not, what's going to happen is, Maggie, If it's not, then you're gonna run into issues where you have to constantly keep reprogramming games. What's wrong? Okay. So okay, 1 sec.
You're good.
Come on.
This is why I'm a cat person.
Stay there. Stay there. Good girl. Okay. So basically what's going to happen is if you're not making your game configurable, you have to reprogram a bunch. And so at the Brain Game Center, you're basically making a data-driven game always in the Unity engine, which isn't too hard. You can use scriptable objects to handle a lot of the data, and you can make custom inspectors, and life is a lot better. But then after that, they have staff there that work there full time, and students that are just like yourselves, except they're getting course credit while they work there. And they're getting to run the study, and then you have someone analyze the results. And maybe if you're lucky, you're going to actually get a paper out of it, but it's hard to say till you actually see the results. And so what a game for research is going to need, and just any study in general, is you're going to need some kind of configuration management. So this is essentially A/B testing in a lot of ways. And so you're going to have a very simple version of the game usually, which is like your baseline, and a more amped up version of the game, which is designed to be as fun as possible, for example, and you're comparing those. You also need user accounts, and you can either go a server-based approach or a local approach. At the Brain Game Center, everything's in iPads, so they do a lot of local stuff, but while I was there, we were migrating over to do a server approach, so you could play on any iPad. And then the third thing you need is logging. And as a programmer, usually the go-to is to create one log file that just has everything inside of it. It turns out while this is the easiest thing to do, it is also the hardest to analyze. So what you end up doing instead is you do a 3-tiered approach almost, where you have like your upper level, which is very high level stuff like how many tasks were correctly done, a second level, which is a task by task like analysis, and the third level, which is very low level like mouse clicks or movements for stuff like that. So you can create like heat maps of where the player's looking at or moving about. And when you actually are making a lot of games for research, what you're going to find is you have a lot of reuse of code, reuse of assets. And you can run into this situation where you have, for example, like 8 different games, and they're all using similar pieces of code, a configuration submodule, a UI submodule, a logging submodule. It isn't just like an engine. It's also just like when you're coding in Unity, you tend to have to write a logging system. You tend to have to write a game manager system or state machine or audio management, whatever it is. So when I got there, we were actually in this situation where all 8 games had different versions of these submodules. And I don't think we're doing this interactively. So the question that you have here is, how do you take it so that you don't have different versions of configurations and UIs and logging, and you just have tools that everything uses? And for those of you that are familiar with Microsoft or Google, the common answer is like a mono repo, right? Where you just have everything in the same place and everybody's developing in the same place. And for Google, they have to implement Google and Microsoft, they have to implement really crazy rules. So like it can actually be stored on one computer. In our case, that isn't an issue because we're not writing billions of lines of code. But what is an issue is you'd have to essentially have one big Unity project. And Unity isn't going to do the best job for you in terms of making the smallest builds, which is actually a problem when you're dealing with the App Store, specifically Apple, because Apple's difficult for everybody. And so a mono repo doesn't work because you're going to have you're just going to have a giant repo for no reason. The other way you could go is a submodule. And in a submodule, essentially what you're getting at is you have one GitHub repo for your common use tools, and every single game is going to be pointing to that submodule, and that's going to be able to use whatever code is in that submodule. So it just points to a commit in the submodule for those of you who are familiar with Git. And when you actually want to update your submodule, you just go to that submodule and you do git pull origin main or whatever branch you're pulling from. So you're basically just pointing to multiple submodules. Some people think it's better to make a different submodule for each of these. So for configuration, UI, etc. But as a general rule, that ends up being a lot more work than it's worth, especially if every single game you're using is going to have this common set of tools. So this is just a really nice way of reducing the amount of overhead you have when moving between games, because before you could be working with 3 different configuration managers, and now you're always working with just one. And if a lot of work goes into one game, every game benefits. The next thing I want to talk about is game flow management when you're talking about games for research. And the reason why it's really important, game flow management, is when you're showing user a stimulus, you want to be very precise in how you're timing their response to the stimulus, just as an example. And so in game flow management, you basically have 3 choices: event-driven, stateless, and stateful. It's just as an example for chess, let's just say for an event-driven game, you can implement chess as it, but for something more complex like Fallout, it'd be impossible to implement because you want real-time updates. So event-driven for almost every single game doesn't work, but you can still do a stateless / event-driven approach. And in Unity, that would mean you're basically using a lot of coroutines. And usually you find some medium between the two of stateful, which is where you're keeping track of the state of the game constantly, and stateless where you're not. But as a general rule, when you want to have tight control over what's happening in the game at all times, something like stateless where you're using coroutines to wait 2 seconds till an object dies ends up actually just being not the best approach, because you can sometimes run into edge cases where the player gets something that they actually shouldn't be getting. And so that's why I recommend, not just for research games, but also just games in general, just to model everything out explicitly with a state machine. This is the basic example of a state machine, where you have a game over state, a game running state, and a game pause state. And then there are events in this example where something will happen, such as the player dying or the player clicking start, and the state will change. And when you're doing this, not only does your game become a lot easier to debug, but you're also in a situation where you are guaranteed, if you've implemented correctly, which is always going to be the case, but if you've implemented correctly, you are guaranteed that whatever is happening, you have complete control over, and there's nothing running on the side that you shouldn't be aware of. So that's why even if you're implementing something like die after 2 seconds, I'd recommend using a state machine and putting it into the overall state machine. In some ways, you're working not with Unity, but as a result, everything in your code is becoming a lot clearer. Which goes to the last few tips when it comes to Unity and general development for the programmers. You want to use assert. There's a common misconception that asserts make your code slow. In the final product, they are compiled out, so you don't need to worry about optimization, and debug builds are always going to be slow, so there's nothing to worry about. There's also this common mistake I saw a lot when I was an undergrad and when I was working with people at UCR Brain Game Center, that they wanted to use the inspector a lot. And I think one of the main reasons you don't want to use it is, I think everybody has probably run into a situation where a scene got broken and you had to reconfigure everything, go into the inspector and change everything to be what it was. And the more you relied on the inspector, the worse that experience is going to be. And in the name of optimization, a lot of people think this is a better approach to use the inspector rather than use like a find object of type or something, which is incredibly slow. But on startup, you're really not that concerned about optimization. It's really once the game gets going that frame rate really starts to matter. So as a general rule, what can be done in code should be done in code. There are obvious exceptions, and don't go overboard with any rule, but that's just my 2 cents on the inspector. Try to avoid it. And in terms of your class design, try to make everything private. It just makes your debugging life easier, and it guarantees that things that shouldn't happen aren't going to happen unless you want them to happen. And then in that case, you're making it public on purpose. Just to reiterate, avoid stateless hacks with coroutines. I just think they're bound to eventually, at a certain point in your project, become a problem once you've reached a certain size. You just need as much control as possible when you're designing these games. And the last thing, this is true not just for game development, this is true for all programming. And that's just, if someone else can't develop in your game, you've made a mistake. There's this, again, I'm going to harp against optimization. There's this common sense that you should make your code as optimal as possible, whether it be in game development or anything else. But until you're seeing frame drops, I really think you shouldn't worry about it. And the only places that you're really going to worry about optimization is if you're writing a big A-star algorithm, for example. But for the most part, just try to make your code as understandable and as reasonable and usable as possible. And only if things get really bad, I think you should go back. But until that point, just try to get the job done, as opposed to try to make it as good as possible. So that's one area of games for research, where you're making a game and you're trying to test it, and you're also trying to make sure that other people can use it in the future. The next thing I want to talk about kind of very briefly is Alphago. A fun story is when I was actually an undergrad, this was a few months before they came out with Alphago, where they beat the game of Go against Lee Sedol, who I think was the third best in the world at the time. My professor told me that just Go was a game that would take 5 to 10 more years to be able to beat a master, and probably even longer to beat the best in the world. And only a few months later, this thing actually came out and just beat Lee Sedol, I think 4-1. And they have since fixed it with AlphaZero, where it can just generally play any board game. That's not completely true. It can play most board games, and but it can't play multiple board games. You have to retrain for different board games. But the reason why I'm bringing this kind of thing up is there's this common, once this came out, there's a lot of people who believe that they should be using neural networks in their games. And what they find out almost always is that it is impractical. So like, for example, OpenAI did a neural network for Dota 2, or similar to League of Legends. And I think it cost them about $700,000 to train their network, if I remember correctly. And for someone like any of us, that's just impractical. And the other side of it is they're training a network that is designed to be exceedingly good at the game. And as the player, that's not very fun to play against. So that's why I'm saying AlphaGo is where they are using a game for research. Even though technically it did advance game AI, that wasn't DeepMind's goal. And they've since gone on to prove that when they did AlphaFold for protein folding. And they've seen some success with that pretty recently. But if you disagree with me and you want to put neural networks in your game, Unity ML agents is a really powerful tool that Unity made. Essentially, you can export your game into something that can be imported by Python. And it's a OpenAI Gym, which is just a common framework for framing reinforcement learning problems. And you can use that in TensorFlow to make a neural network. And then Unity can actually just read that neural network and use it, which is pretty nice. It's being actively developed. The most recent commit was like 15 days ago. So that's usually a good sign that Unity is actually still working with this project. And if you wanted to take it a step further, instead of looking at how you can make an agent play your game really well, you can also look at how people can play with neural networks, which is something that some games have been doing. And a paper that came out of Drexel actually, whereas by Ji Chen and Jennifer and other people, and it's called Player AI Interaction: What Neural Network Games Reveal About AI's Play. It's a really good paper. It talks about how you can create interactions with neural networks as a form of play, kind of like how Black and White had you teach. I think it was a support vector machine, but now we're talking about neural networks. And I think Ji Chen is still a professor, or maybe they're at ITU Copenhagen. But if you are interested in this kind of area of researching neural networks and how they can be used in games, Jennifer Villarreal, or however you pronounce her last name, I did another paper with her, and she's wonderful, and I'm sure she'd be happy to talk to you and help you out with whatever you need or give you resources. And this game and this whole paper actually has a lot of potential games you could play as reference material. Okay, so the next thing I'm going to talk about is research for games. And in research for games, I think there's three topics that are pretty relevant. There's playing games, which is what we kind of were just talking about. There's modeling players, and there's generating content. So in playing games, you have basically two modes. You play to win or you play for experience. In Alphago, the research was to create an agent that could always win, but that's not really what you want for a game. So in Civilization, for example, you don't want an AI that's always going to beat the player. You want an AI that's going to be interesting for the player to play against. And it doesn't even have to be smart under the hood. It just has to appear reasonable and not do dumb things. And if you can do that, then your AI is probably going to be set. Doing that is very difficult, which is why a lot of game AI practitioners will say you should use utility-based AI. And I could send you some stuff on that if you'd like. I'm on Discord, by the way, if you want anything like that. And the other option is play for experience. And there's this actually really nice YouTube video. It's 17 minutes long, and it's in this channel, AI and Games. And it's called The Secret AI Testers Inside Tom Clancy's The Division 2. And it's just a 17-minute video, and they talk basically about how these AI testers are used to go through the entirety of the Division, which is a very large world that they've made with a lot of potential things to happen. And the goal of it is basically to find bugs. That's all these AI try to do. And they did it partially probably because they didn't want to hire as many QA people, but also because there's no way QA can cover everything in the Division. So when you have a world that big, then you turn to AI. And they are able to actually find a ton of bugs, and they talk more about that in the video. But that is one reason why you would make an AI for experience, where you're trying to discover things about your game. That's something also No Man's Sky did, where they basically had a probe that just flew through their entire world and tried to take screenshots that seemed relevant. That's one other way to look at it. The other area is modeling players. And so in modeling players, the goal is predict what the player will do next. The goal, though, is once you have this player, this model is to understand how the game is experienced by an individual player. And the question is, if you have a model that is accurate, what do you do with it? And there basically is an offline and an online approach that you can think of. In the offline approach, you're basically going to be analyzing these models and what they would do outside of the game when it's running, and try to figure out how you can improve your game. And then you're going to basically make a patch, upload it, and then see how the player models change and keep going. The online approach, which is I think a little bit more interesting, is use these models to actively respond to the player. So in that case, you'd be like generating content, maybe making the difficulty level easier or harder, depending on how the model seems to be behaving and things like that. And as a general rule, player models are going to be built with neural networks. Sometimes they're built with simpler methods like linear or logistic regression, but generally you just throw this like black box neural network in and let it figure it out over time. On that note, though, when it comes to modeling players and neural networks, there's a lot of ethical concerns that people have brought up. I'm not an expert on those, but there's a lot of research on it, just on AI, fairness, ethics. And if you are going to be modeling your players, it's something you should spend some time in and consider. I personally I haven't done any work in modeling players, so I haven't spent the time to research it yet, though. What I do spend my time, though, on is content generation. And I've made this one green specifically because I spend a lot of time on level generation. But you can also do maps, textures, stories, items, quests, music, characters, and even whole games. And there's more, of course. You could just generate trees or whatever. And there are 4 examples on this side. The first is Rogue, which was procedurally generating like dungeons, just so you could get from any one room to any other room. This one below is using L systems, and L systems are used to generate trees in AAA games. And the reason why they're doing that is because it is a little ridiculous to actually have 100 different trees in your asset resource database. So instead, you just use an L system to generate it, and it's very fast and efficient. And you also don't get that storage hit. Facade is just a really interesting game, and if you haven't played it, I recommend it. Essentially, you're interacting with these two AI characters, and it is generating what they're going to say based on what you've said and how they're going to act. But there's still a limited set of endings. So even though there's this like very expansive middle, the end always is going to come to like a few different endings, but it's still very interesting. And this board game over here is called Yavalath. And this is actually the only published board game that was made by an AI. I think there actually may be one more, but it's made by the same guy. And the basic rules of it, the rules of it are very simple. It's Connect 4, except you cannot have 3 pieces in a row. And if you do have 3 pieces in a row, you lose. And it's a 3-player game. And that's the only published board game to have ever been made by an AI. So we're going to talk a little bit about level generation because that's what I spend my time on for the most part. And you'll notice a bowl of oatmeal and Mario. Those are the 2 biggest problems with procedural content generation research, if you'll believe it. And we're going to start with oatmeal. And this is actually a problem that was formulated by Kate Compton. I believe they're at UC Santa Cruz still, but they may have moved since I last checked. And it's a little 2-page PDF called Ways That Generators Fail that I'd recommend you read if you're interested in procedural content generation research. And the basic way the problem is formulated is you have these 2 bowls of oatmeals, and you can make 10,000 different bowls of oatmeal, and they may be different, and you may be able to spot the difference. Like in this one, I can tell this one's a little higher, where this one is a little lower. But as a general rule, as a player, I don't really care, right? I don't care that there's 2 different bowls of oatmeal. It doesn't really change the fact that it's going to taste the same. It's going to have the same texture. It's everything about that oatmeal to me is essentially the same as a player. And just to put this in more reasonable terms, if you remember Infinite Skies when it released, they were advertising they had like a quadrillion planets. But a common complaint was from planet to planet to planet, nothing really changed between the planets besides minor details and basic colors. So there wasn't actually a reason for you to actually care about the generator because it wasn't doing anything that you thought was interesting. It wasn't making it different. It wasn't making it more fun, less fun, more jumps, less jumps, whatever it is. It was basically you were just getting a different bowl of oatmeal. So that goes into the question of what actually makes a level different. I put in color palette because sometimes that can actually be enough if you're doing it well. Like you can just change it to an ice world and it will feel very different to some players. But as a general rule, you want to follow something called behavioral characteristics. And this was made by Jillian Smith and Jim Whitehead and Michael Matthias. And this was when Julian Smith was a PhD student at UC Santa Cruz. And the basic idea is you look at a level and say what makes it different. So for Mario, it'd be coins, enemies, jumps, etc. For a different game, it may be number of doors, number of keys, number of cannonballs, whatever it is. And you use that and you can classify pretty reliably, well, 100% reliably, how different a level is from any other level in a game. And so in this example, I have a level being classified based on density and leniency. And leniency is how hard the level is, and density is how filled the level is with solid tiles. So as you can see, it's very hard to make a highly dense and highly lenient level, which isn't that surprising. But when you're trying to classify these things, you have to make a generator to actually fill in this space, which is why you get the expressive range of a procedural content generator. And that's really what you're after. You want a procedural content generation system that can generate a lot of levels with different behavioral characteristics. Otherwise, you're probably in the realm of the bowls of oatmeal problem again. The next big problem with procedural content generation research is Mario. Now, I'm sure some of you are familiar with this guy named Notch, created Minecraft and has since become problematic. around the mid to late 2000s, he created a version of Mario 64 in Java. And Julian Togalius, who's a researcher at New York University, thought it would be a great platform to test game playing AI, test procedural content generation, and create a competition. And as a result, this framework that Notch made ended up becoming heavily used in the procedural content generation and just general game AI research area. And it is still heavily used today. There are papers that have come out in the last few months that are still using Mario. And it's problematic because a lot of procedural content generation research only is based on Mario, which is a very simple 2D tile-based platformer. So you're not seeing a lot of research in like 3D games, for example, right now. But at some point in I think like 2014, Nintendo actually struck down Notch's repo. And then a little bit later, Ahmed Khalifa, a PhD student at New York University, created a new one called the Mario AI Framework. So if you're interested in PCG research and you want to replicate some stuff people have done or do your own thing, the Mario AI Framework is actually a good place to start, even though it'd be cool if people started using other games. That being said, I've used Mario in my own research, so I'm a hypocrite in a lot of ways. All right, so when we look at the PCG like area, if you will, there's also, just because people are only using Mario isn't necessarily for a bad reason, because there's not a lot of games that also have their data publicly available. So for example, you wanted to create a PCG system for Obsidian or something like that. There's not actually a lot of data you could get from them. So with the VGLC, or the Video Game Level Corpus, and this is by Somerville and also Santi, I'm not sure if he's still at Google or if he's now a professor again at Drexel, but he worked on this paper too. And what this does is it has like 10 or 15 games that they basically by hand turned into little text files that you can use to actually work with for PCG research. And that's one way that they're tackling the limited data problem in PCG, where there just isn't a lot to work with. And speaking of not a lot to work with, there is actually this central tension in all of PCG, because ultimately we're making PCG research is for games and for game developers. But you have to actually convince game developers to use the technology. And one of the problems with trying to convince people to use it is that what we're doing is we're asking them to make levels in their game and then feed it to an algorithm that will then feed similar but maybe different levels. So there's this central tension in that you need to create a lot of data for a game, and you also need to create a lot of data for a PCG algorithm. So what's actually the benefit of the PCG algorithm in the first place? And that's a hard question to answer. Some people will say there are no benefits. Some people are saying that we're making progress and time will tell. One promising approach is instead of actually asking the designer to make new levels, instead ask them to come up with a blend of the game that they're looking for. So this comes from Anurag and Seth Cooper, who's actually my advisor. And basically what they looked at was how they could combine, I believe, Mario, Zelda, and one other game that I'm not, maybe Kid Icarus. I think Kid Icarus. How they could combine these three games to generate like dungeon-based games. And so that's a promising area, but it's also very difficult because you're not only blending levels, you're also blending mechanics and a lot of other things that make it very difficult to get right. So as a whole, PCG is a very difficult field to work with when you get to the more modern stuff, but some of the more basic stuffs like you see in the original Rogue game are very usable even today. So now that the overview is through with, I'm going to talk a little bit about my work in PCG and hopefully keep the technical details to a minimum so it doesn't get too boring and too technical. So This first paper is out. It's Grammalytes n-gram-based quality diversity search. Maplates is just a genetic algorithm, and it's just going to generate a large corpus of level segments. And it uses genetic operators called crossover and mutation. And all you have to know about those operators is they take a level and they change a level by moving things around. But what they do is they don't move things around intelligently, and they don't actually respect the game. So for example, in Mario, there's a chance where it can move a pipe around, but it's not going to move around the whole pipe. It's going to move around one part of the pipe. So you can end up with levels generated by this that have pipes all over the place, but they're not complete pipes. So as a result, you have to start implementing filters. So you guarantee that the results are going to actually be filtered to actually include what you want and that respect what the game is actually trying to do. So Maplates, as a general rule, is going to waste a ton of computation, and it's going to find suboptimal results due to these genetic operators. So what this paper does is it created two new genetic operators, which essentially guaranteed that when something is moved around, the game's basic rules aren't going to be respected. So pipes in Mario, doors in Icarus, stuff like that. That's the idea. The result we got was the new approach, Grammalytes, found more levels with fewer iterations than Maplates and one other baseline. And so basically what you get when you run this kind of algorithm is you can get like 500 level segments that you can use to generate larger levels, or you could just generate large levels from the start. And we ran this algorithm for 3 games, Mario, like I was saying, Kid Icarus, and we used the horizontal platforming levels. And because we wanted to show that it just doesn't just work for a platformer, and platformers are pretty much ubiquitous in PCG research right now, we also made this small roguelike called Dungeon Grams. And on all 3 games, it outperformed Maplates and one other approach by a pretty wide margin. I don't know if I show the results. I don't think I show a table in this presentation. Yeah, I don't. But yeah, so that's the first paper. The second paper, which is done, and we're just waiting for a conference to start allowing papers to be submitted, is tentatively titled On Linking Segments. So basically, when you generate a lot of level segments in Mario, what you're going to find is that you can basically just connect the 2 levels by concatenation, by just squash them together. And the game's going to still be playable without any problems. But with more complex games, that just isn't the case. And you need a better solution that works for every single game rather than just Mario. So the goal of this paper is to link level segments such that a larger level is both playable and fits within the constraints of the game. And just going back to the Mario example, imagine if this level segment ends with a pipe. If you try to connect another level segment that also isn't starting with a pipe, you're going to have a broken game, basically. So you want to find a way that is both going to result in 1, playable, and 2, unbroken structures. And the way we're going to solve this is we use n-grams to guarantee unbroken structures, and we use a tree search for playability. So the tree search is basically just searches if it needs to add any extra tiles to get the level to be playable. And the result is that our approach consistently finds links for level segments. Just as an example, in this one, you have concatenation, and you can see the player would have to jump along here, probably jump along here. I'm assuming you can see my mouse. But then at this point, it's just too large of a jump, and the player is going to end up having an unplayable level. So that's why you kind of want something like on-linking level segments. And in this case, what it did was it just added one single tile so the player could actually make a longer jump and complete the level. In terms of the results, for those that are interested, in Mario, it's 98% chance or 92% chance that any level that you combine together are going to be completable. And then in terms of unbroken structures, it's 90%, whereas with our approach, it's 100%. With Icarus, which is a very difficult, it turns out to be a very difficult game to solve. it's 13% chance when you're using concatenation, but our approach is 100. And dungeon grams, it gets down to 97%. And that's because there's a food mechanic where you need to get food every so often. So sometimes it's not possible to link them without, at least with the linking segments we provide. So that takes me to the last work. And this is where all the work is leading, which I think is the actual interesting part. And it's forming larger levels for dynamic difficulty adjustment. Again, it's a work in progress, and the title is also work in progress. And so essentially in the past two papers, what we've done in the first paper is we created level segments like A, B, C, D, E, F, G, right? In this node, this like graph, if you will. And then the links determine if a transition is valid, right? So if A can go to B, if a link is valid between the two, then that link can exist. If not, then no. And what we want to do is we want to connect these to form larger levels. So 3, 4, 5. And the reason we want to do that is we want to be able to form levels that are of the appropriate difficulty level for the player. So that's where the dynamic difficulty adjustment comes in. And to do that, you basically need to do a some kind of reinforcement learning process. And you can formulate it as a Markov decision process, for example. And I'm not going to go into the details of that. But once you have this graph set up and you have an agent, whether it be a model based with value iteration, policy iteration, or model free with Q learning and SARSA, this should be all capitals. You can basically run an agent through it, and you can run a study. So our study is going to be, once everything's implemented, to use level segments and links to form larger levels based on how the player is playing. And then what we're going to do is we're going to use an RL agent to find the optimal policy for a player given a graph of level segments and links. Now, the result is to be determined. And I think one part that is actually exciting about this particular work is that it actually doesn't have to be 2D, 3D, or any kind of game type. All you have to do is have level segments and say whether or not they can connect. It could even be used for Spelunky for people who are familiar with Spelunky's level generation system. And there's some questions, obviously, that we want to be able to answer with this work. And one thing to note that is why this work could be really interesting is that there is other work that has looked at generating larger level segments, larger levels, sorry. And basically what they found was that if they actually wanted it to be usable, the player would have to do about 200 playthroughs for it to actually adjust to the player properly, which is, it's interesting and it's a step forward in the research, but it's not usable at all for game developers. You can't ask a player to play their game 200 times before they get an experience that's good for them. So the question we want to answer is, how quickly can a reinforcement learning agent learn an ideal policy from a player? And the other question we want to answer is, how quickly can the agent adjust to a new player? So if, for example, the player had been playing, if, for example, AJ had been playing the game for a day, and then Frank came on out of the blue and just said, I want to play, would the game be able to adjust to Frank not being as skilled? No offense, Frank. I'm sure you're very good. But that's kind of what we want to get at. And so the research goal is less than 100, but in reality, it's not even usable if I think it's not usable unless it's less than 5, in my opinion. So that's what we're after in this kind of recent work in progress. And in the next week or two, I'll know if it actually works. And then, yeah, so hopefully it does work though. And so that's kind of been the presentation on research for games and games for research. So yeah, thank you for your time. And then the one other thing is, if people want resources, I think these two books, Artificial Intelligence: A Modern Approach and Artificial Intelligence in Games, are really good. And they're great starting points if you want to get into game AI research.
That's also cool. Thank you. Let me check the time. Okay, so we have about 14 minutes left. Frank is edging up here. I assume he has questions. But if anyone else has any questions and wants to like, either if everyone could like come up and make a line if you have questions, or we could just raise hands. By coming up would be easier. So
because the microphone's here.
yeah. Does anyone have any questions that you'd like to ask him?
So I mean, I'll start off to give people time to think about the questions and so on. Yeah. So Colin, thanks a lot for sharing information about your research and so on. In particular, the bleeding edge research that you and people, I guess, similar to you within the area of trying to meld AI and games, especially on content generation, I think is really cool. Because the one aspect about those type of AI is that you're not trying to create the AI that's perfect. You're trying to create the AI that's human-like, right? You're trying to create levels that people, developers will create. Right? So I think that is a sort of difficult area to explore. So the type of work that Colin and people within that research area are doing probably won't be something that you will see within games in the next 10 years or possibly next 15 years, but something on long term. Hopefully that will still come in to games. So a couple of questions I have, especially for the people in the EGS. One, how did you go from just kind of passively taking classes at Drexel and then potentially thinking about research and grad school as a path, as a career path? So that's one. And two, can you tell us a little bit more about your sort of day-to-day life as a grad student? So what do you do, and so on? So kind of so those two questions I think would be kind of interesting.
Right. So how I wanted to get involved in research. It was through the co-ops. Partially, I did a co-op at iPipeline, which is like this middleman insurance group. And I didn't enjoy that very much. And then I looked at the games industry and I saw all the crunch and that kind of stuff, and that didn't look very fun to me. And so yeah, I was thinking of going into grad school at that point, but I wasn't really sure if I really wanted to. And then I was graduating and Frank gave me this opportunity to go over to Aaron in the Brain Game Center. And while I was there, I was mulling over it, and it just seemed like the right thing for me to do in terms of the work I was doing there was interesting. I liked being in a research environment, and yeah, it seemed like the best of both worlds. So I went to Northeastern to work on my PhD. And the other one, what was your other question, Frank? I'm sorry.
So the other question is what is a typical
typical day
like? Yeah, for EGS grad students.
Yeah, you're looking at it. Pretty much directly. I sit at this desk. I could go in, but for the most part I don't because of my dog. My dog just is right there for most of the day, hanging out, not barking, like the beginning of the presentation may lead you to believe. When I was in classes, it was a lot more going around campus, but I don't know for all schools, but you take 1 to 2 years of classes, generally speaking. Some schools have qualifying exams, some don't. And then the typical day is I'm either reading papers, reading books, or implementing stuff. And there's the occasional meeting with the advisor or people in the lab. And yeah, that's a typical day. You start off and you just start working on whatever you're working on, and you get to choose what that is. So that's kind of cool.
Does anyone have any questions they'd like to ask? No? All right. Well, I know a lot of people have to run to class in a few minutes, so I don't want to hold them up for too long. But thank you so much again, Colin. This is so cool. I guess one more round of applause. Thank you so much.
Thank you.